Hi everyone, welcome back. We've been talking about statistical significance for a couple of videos now, and I think it's important that we now introduce something called statistical power. It's related to statistical significance, as you'll see. All right, when we have statistical significance, what we're essentially saying is we think that these two variables have some relationship. One of them seems to affect the other one. And I'm comfortable saying that with a low chance of error, okay? In fact, specifically we say there's a 5% or less chance that I'm making a mistake by saying that, okay? Now, what I'm saying in terms of the type 1 and type 2 errors is I'm saying I have a low chance of committing a type 1 error when I go ahead and say that I think these two things are related. And of course, you'll remember a type 1 error is a false positive, meaning it actually isn't true. That's very important. That's great. However, we need to also think about that type 2 error. Once again, the type 2 error is a false negative. It's when you say these two things aren't related, but actually they really are, and you just didn't know it or you weren't able to find that with your research design. So when we have a non-significant result, we want to make sure that that really is true, that these two things actually didn't affect each other. That would be a big mistake and a problem and potentially cost lives if we said that these two things aren't related and in reality they are. Imagine, for example, a medication that's actually effective at higher doses, but we just didn't find it in our study because we weren't giving people in the experimental group that high of a dose. So if we don't find an effect that really is there, that's a big problem. So what's important here is we need to have enough statistical power to detect an effect of one variable on another. So let's talk about that a little bit more. Statistical power, sometimes also just called power, is the ability to detect the effect of one variable on another variable if there really is an effect of one variable on the other. Now, of course, a lot of things go into that and just how much ability you have to detect the effect of one variable on the other. But I'm going to go with an example now. Let's use sort of a solid example so we can apply some of this as we go, and hopefully that'll help to learn all this. So let's say you've got somebody named Violet. Violet's a researcher in nutrition. Violet thinks that she can influence people's cholesterol levels based on how much processed food they eat. Okay, so basically what she does is get some volunteers, kind of a small group, 7 of them. She says, please very carefully adhere to this experimental diet that has very low intake of processed foods. And then the other 7, she says, just don't do anything differently, right? So imagine that. And then 6 months later, she examines their cholesterol levels and finds that one of the groups does have lower cholesterol, but it's not statistically significantly lower. Okay, so now there are a couple of things that could go on here. So first of all, she didn't find statistical significance, meaning she doesn't have enough evidence to say that her manipulation really worked. She can't go saying, hey, everybody, I figured out how to lower people's cholesterol. So there are two possibilities that happen here. Either her diet really didn't work, right? Her diet didn't affect people's cholesterol level at all. That's possible. Maybe it was just a failed attempt. Nice try. That's great. We learned something. Or maybe her research design just wasn't able to find the effects of that new diet on the variable. In other words, using our terms here, either it didn't, there was no effect, or there wasn't enough statistical power to detect the effect of her independent variable on the dependent variable. Now, in Violet's study, there may have been several things that could have hurt her statistical power and therefore ability to detect an effect. For example, one thing that you may have noticed is that she had a relatively small sample size, 14 people spread across 2 groups. That's 7 people per group. That's not very big, which means that there's a lot of noise that's unaccounted for in the sample. And another way to think of it is the means of those distributions aren't very well defined because the people are so different from each other. You don't have enough people to represent the populations for which they stand in. Okay, so increasing your sample size is one way to increase your statistical power. There's a weakness there that we'll talk about in a moment here, but that's important. Also, anything that decreases the variability or the variation among your sample on that dependent variable will also improve the power. Now, that's kind of a complicated sentence, but let me give you some specific examples. So you could, for example, get people in your participant pool who are more alike each other. In other words, they just differ from each other less on all sorts of measures. That could be particularly useful. For example, people are going to differ quite a bit on all sorts of measures if they differ on age. Okay, their general health probably, maybe even their world experience probably will differ quite a bit. Their income levels will probably also differ due to age and things like that. And so that's something you might want to consider as you say, instead of getting anybody who's above 18, for example, why don't we just get people who are between the ages of 30 and 35? That way they're going to be more similar to each other in several ways, probably including in their health. Another one might be race, gender, health, all sorts of other things that you could measure people on. You could start to collect people and put them in your sample in ways that they are more alike one another, therefore differing from each other less. That will decrease the variability that's already there and therefore increase your ability to detect an effect if it is there. Essentially what you're doing is decreasing the noise levels around these variables and trying to get a really precise signal, if you will. You could also do other things to your actual study rather than changing who you're measuring. For example, you could do a better job creating a measure and the way that you're measuring this kind of variable. So for example, you could make it very clear what you're measuring to people instead of course kind of leaving meanings ambiguous on measures, for example. So one example I like to use is in classes and in my textbook, I say, for example, let's say that you ask a bunch of people, have you ever broken the law? And of course, people will be confused about what you mean by that. Do you mean a felony? Do you mean was I ever convicted? Do you mean is speeding when I'm driving breaking the law also? Is that all considered? Because then probably everybody would say yes. And so if I leave confusion, people are interpreting the question differently, and now I'm not getting a precise answer that I want, right? So you need to be very precise in what you're asking and say, have you ever broken a law that would have been a felony had you been caught and or convicted? Now that's much clearer, right? And people can, there's less room to interpret that incorrectly. So you could do things like that. You could also decrease the number of answer options. Anything that's going to decrease the standard deviation on that measure, on your dependent variable measure, is going to be helpful for increasing your statistical power. Another trick, which is not really a trick, it's a study design issue, although you could manipulate it and use it incorrectly, of course, but is to increase the strength of your manipulation. For example, in Violet's case, she could have changed the diet even more. Instead of saying, you people don't do anything different and you people please be careful, she could actually control their diet specifically and say, I am going to give everybody these prepackaged meals. You are not allowed to eat anything outside of these prepackaged meals, and you have to eat these prepackaged meals on the schedule I give you. And then the other people, you're going to eat these other prepackaged meals that are highly processed, for example. And so she would have even more control and also increase the strength of that manipulation. Another way to think about that is to increase the dosage of the treatment. For example, it might be if I'm testing out a new medicine, instead of giving 3 milligrams at a time to the control or to the experimental group and nothing to the control group, maybe give them 15 milligrams, maybe give them 30, depending on, of course, the efficacy and the potency of that drug. So, of course, generally you'd probably want to start off small, but if you're not seeing the difference, increase that dosage perhaps to increase your statistical power, as we say. And there are, of course, lots of other things you can do, but really anything that's going to decrease the variability and also give you more precision in the estimations of the means is the way to do it, at least in a means comparison. Let's take a look at this visually using a histogram example. So let's imagine that this is Violet's sample, right? She had 14 people and she graphs them. And so the people in the control group are represented here. This is their cholesterol levels, right? And the people who tried her diet with the lower processed foods are in the yellow group. Now, let's imagine she had a relatively high standard deviation. We hadn't talked about that before, but that's fine. And I'm probably exaggerating this just a little bit, but I hope this will make the point. So imagine that this is what's going on and you're a t-test. Let's anthropomorphize the t-test for just a moment. The t-test looks at this, mathematically obviously, and says, gosh, yeah, I can see that these are different, right? This one's clearly higher, this one's clearly lower. But look at how widespread these are. People just had their cholesterol levels were kind of all over the place. That's very high standard deviations, large standard deviations. And because they were just so different from each other anyway, there's so much overlap. I'm not comfortable saying that the diet worked. I just can't do that. I'm not comfortable doing that. Okay. Now let's contrast that with something with better power. Let's imagine we increased our sample size. So here's our increased sample size, but I kept the standard deviation the same. In other words, I spread these out the same as in the previous example. But with more people, now I get these highly or more defined peaks anyway. Now this might be where a t-test finally says, okay, I mean, yeah, there's still a lot of overlap, but it's getting to the point where I think it's safe to say they're different, okay? So in other words, I'm getting more statistical power. I'm getting more the t-test more comfortable on making a call here that would reject the null hypothesis. All sorts of ways to say the same thing, right? Now let me give you an even higher example of power. What I'm going to do here is decrease the standard deviation. Here's the same thing, means are the same distance apart, still large groups, but I've decreased the standard deviation. Now when I do that, I have very clearly defined peaks, and there's a lot less overlap between those two distributions. And so therefore the t-test could look at this and say, oh yeah, I mean, this is plain as day. There's definitely something going on here. Look at how clearly defined these peaks are. They're not overlapping a lot, and therefore generally most of the people who were in the control group had higher cholesterol than the people in the diet group. It's so easy for me to go ahead and reject the null hypothesis at this point. In other words, this kind of design, this kind of test, this kind of data would have high statistical power. And again, there are lots of ways to do that to decrease that standard deviation, as I talked about. Okay, I need to make a point really quickly before we move on about the abuse of power. If you are a researcher who takes all steps available to you to increase the statistical power of your test, what you can do is essentially get to a point where it's impossible to retain your null hypothesis. In other words, you are guaranteed to find statistical significance. Imagine, for example, that I did an independent samples t-test, but in one of my groups I had 1,000,000 people, and then in the other group I had 1,000,000 people. That's such an enormous sample size that there's simply no way I'm going to be able to retain my null hypothesis that says they're equal means. You're going to get enough general variability that you're going to find a difference there, essentially. Now, some people might argue that's not a problem because, in fact, Jacob Cohen, the famous statistician, I believe it was him, said that the null hypothesis is actually always false in reality. That's interesting because it's essentially like the butterfly effect, you might think, is that like a little butterfly's movements don't seem to affect me at all, but actually they affect me very indirectly, or they'd have a huge impact on the future or something. That kind of idea, and that's what Jacob Cohen was essentially saying. So if you abuse your power, you're always going to find some effect of the butterfly wings movements on me, for example, on how much coffee I drank that day or something, if it gets big enough. Now, the important thing there is that we want to be very cautious about that. We don't want to therefore tell everybody that, oh yeah, it's statistically significant, because that can be misinterpreted, as we've talked about before. So what we want to do is also, as long as we're increasing our power, we have to also report our measures of effect size. That's what's important, because the butterfly effect may be real. Maybe that butterfly's wings really do influence me, but it's so very imperceptible that I can live my daily life without worrying about what the butterfly's wings are doing, right? That would be a very tiny effect size and an almost negligible effect size kind of thing. So it's very important. Not only are we reporting statistical significance, we're also reporting the effect size. Okay, quick summary of what we talked about then. Statistical power is the ability to detect the effect of one variable on another if it really is there, if there really is that effect in reality. And as I said, Jacob Cohen argued, at least, that there always is that. It just may be so subtle we can't pick it up otherwise. Anyway, another important caveat is that even if you have high statistical power, then relatively high statistical power, it doesn't mean that you will find statistical significance. Of course, you can abuse your power to that point. That's where we need to be very cautious about that, however. If you're a good researcher, you want to be cautious and try to not maybe stack the deck entirely in your favor, as it were, and instead find what's going to be most useful, most reasonable, and most appropriate for this kind of variable that you're using. Okay, and therefore reducing unaccounted for variability in your samples, in your study, will also increase your power, but we need to be cautious, as I said. So always report your statistical significance and then right next to it your measures of effect size so that we have some measure of practical significance. Okay, thanks, that's it for now, and we'll get into a new topic next time.